We want to determine how these quantities change as a function of position, as a function of time. To do that, we need to solve some equations. We'll try to build that equation. To do that, let's just consider a situation where you have uh, basically a semiconductor. Let's call it an N-type semiconductor. Okay, you could easily take a P-type semiconductor. There's no difference at all. So an N-type semiconductor, okay, and it has a doping, some doping. Okay, right now I don't need to worry about what is the doping, and I will shine light only at, I'll apply a light pulse. Okay, so only at x equal to 0, right? Some position. This is position x. Okay, at position x equal to 0, I apply a light pulse, and then I create excess carrier density, which is equal to delta P naught. Somehow, just shine light only, focus it only at such certain section of the semiconductor. So now what happens? Okay, well, you create the other places you have. Well, delta P naught might confuse you, but essentially I'm saying that delta P naught is at time t equal to 0. It's not the changes in the P naught. P naught is the equilibrium carrier density, right? But delta P naught means that delta B at time t equal to 0. Okay. So now what happens? Well, at other locations in the semiconductor at time t equal to 0. Okay. At time t equal to 0 here, I mean away from the semiconductor, away from the x equal to 0 point, delta P is equal to 0 because it's at equilibrium. There is nothing that is disturbing, right? At t equal to 0 for, I'll put it in, this is only for x less than 0 and x greater than 0. At x equal to 0, we are having exactly delta P naught. At every other place, there are no excess minority carriers. So there is a concentration gradient, and we saw that there is a diffusion process that happens, right, whenever you have such a situation. So what will happen is the initial, if I plot out, let me plot, this is delta P versus x. Okay. So initially at time t equal to 0, I have my carrier density, minority carrier density, p-type, right, n-type semiconductor, so delta P at x equal to 0. Let's say this is the number of holes that I introduced. Now, as time changes, what's going to happen? These things are going to diffuse, right? So what I need to do is essentially monitor, for example, I can monitor a location maybe here, at some x equal to x naught. I'll try to monitor what is the number of holes. Okay. So because there is a gradient, the holes are going to diffuse, right? It is going to diffuse. And it will cross the surface, this x equal to x naught, right, at that particular surface. So I'll try to monitor what is the rate at which the minority carriers are crossing that surface, and that I'll denote it by partial derivative of delta P with respect to time. Okay. So excess minority carrier at x equal to x naught is going to be changing with respect to time, and that I'll represent by this. And it turns out that this is a diffusion problem. This is a very classic problem that is introduced probably in +2 for some of you. If not, just look up Wikipedia, and it's a very straightforward problem. So what this tells you is that whenever you have this diffusion-like processes, the excess minority carrier concentration is going to be dependent on the diffusion coefficient times the second derivative of delta P with respect to space. So this is the diffusion equation. Okay, this is called as a diffusion equation. So what this is telling me, remember, this is first derivative, okay, with respect to time, and this is second derivative with respect to x, and the coefficient that is linking is the diffusion coefficient. This is the same diffusion coefficient which you saw in the diffusion process. We wrote the current density as product of diffusion coefficient times the gradient. If you want to look at the time change also, then you could do this. I mean, they are all interrelated. Okay, so this is the original equation. From that you can derive the current densities and so on. All right. So this is your diffusion process that's happening, right? So if you just shine the excess minority carriers, then just if you create this excess minority carriers, they'll simply diffuse. In addition, we've also been talking about the recombination process, right? Let's say, what happens to recombination? How does that happen? We want to monitor how the minority carrier density changes with respect to time. So let's write it as partial derivative, same partial derivative with respect to time. So over here, if I call this as equation one, I'm only talking about a diffusion process. Okay, but definitely we know that there's going to be recombination process that also has to be accounted for, and that's why this is going to be partial derivative with respect to time of delta p, the excess minority carrier density. And whenever you consider recombination process, we know that it is going to be proportional to the excess minority carrier density delta p. Think about it. How will be the rate of change of minority carrier density? Will the minority carriers increase with time or decrease with time? Okay, because whenever you are recombining electron and holes, your minority carrier density is reducing, right? So your proportionality constant should have in this equation should have a minus sign. Okay. To denote that you have a decrease in the rate at which the minority carriers are changing with respect to carrier concentration. Okay. And if you write out the actual equation, if the proportionality constant, you could actually solve it. And the proportionality constant turns out to be partial derivative with respect to time is equal to minus delta p divided by tau p. So what I'm trying to say is this proportionality constant, which I call as minority carrier lifetime, time, and if you solve this, you will see that actually delta p is going to be some delta p naught exponential. I'm writing below. Okay, so delta p is going to be delta p naught exponential minus t by tau. So that's why I wrote in one of the previous slides that this is basically an exponential decay. Right? So you have time here, and this is going to be delta p. Essentially, you're going to have an exponential decay. Sorry, my explanation is poor. Right? So this is delta p naught. So this is how minority carriers will change. Okay. So these are the main processes. Okay. So what we'll do is we'll try to sum them up into a equation which we call as minority carrier diffusion equation. This is something that you will see many places. Okay. So what we did is, we're just recapping. We are saying that excess minority carriers concentration plays a very crucial role, and the diffusion equation that controls that can be written in this form. So we are combining both the diffusion process and the recombination process. So this is basically time variation, right? Time This is basically time variation at a particular position. How does the minority carrier density change with time? That is going to be dependent on the diffusion process and the recombination process. Okay. And for completeness sake, of course, I didn't really describe it, but it also depends on the generation rate, right? We are only talking about how they are diffusing once they're created, but then you also, if you're talking about time dependence, you also have to include the generation rate. And that is what we call as excess minority carrier diffusion equation, MCDE. Okay. This is for n-type semiconductor. If you have an n-type semiconductor, you have delta P, which is a minority carrier. P is a minority carriers, and we will write it for minority carriers. If you have a p-type semiconductor, you will write it for n. Okay, and that's why this is going to be tau n. This is going to be tau p here. So remember, all of the coefficients, everything is going to be corresponding to only the minority carriers. Okay. I should also point out, this is a simplified version. Okay, if you want to actually solve it in devices, you also have to take into account what happens with the field. Okay, because your diffusion process is going to be affected by the field, right? That is an additional variable which I have not really taken into account. Well, I mean, if you want to do that, it becomes a little bit more, it's complicated and we don't gain much out of it right now. So for the physics necessary for understanding the operation of the devices is this. I mean, if you understand the spatial and the diffusion and the time dependence, that's enough. That's why I didn't put in the field dependence part of it. Okay, but it is still there. I mean, in the real devices, because you are definitely going to have introduction of minority carriers, and then there will be some field also applied. So the diffusion process is going to be accelerated sometimes, right? So you have to see that as well. Okay. Anyway, okay. I also want to point out one specific case. This equation is valid essentially for what we call as low light injection. Okay. Low light, not low light, low level injection. By which I mean that if I'm introducing this, the stimulus that is introducing this excess minority carriers is such that the minority carrier density itself is quite small compared to the majority carrier density. Okay, the majority carriers are n naught, right? They are significant in number. We are not reaching a level where you're reaching the minority carriers are reaching that level. Suppose if you consider a situation where delta p is of the order of n naught, the majority carrier density, then this is called as high level injection. Okay. Then something's changed. I mean, because we have to have a few more processes that have to be accounted for and all that. Okay. Anyway, low level injection means that minority carrier density is much smaller than the majority carrier density, but still it is significant compared to the equilibrium minority carrier density. So delta P is greater than P naught. Similarly for holes, you have the same relation. Okay. So this is what we will consider. If not, then we have to do some corrections. Anyway, so this is a background, what we need to solve. Let's take a few examples and try to solve them. Okay. With that, we will know how to interpret the result. Okay. So now let's consider one case where you have a semiconductor. Okay. I have a semiconductor and I'm illuminating that semiconductor with light. Okay. Let's assume that this thickness of semiconductor, if I assume this is the thickness of semiconductor, okay, I'm drawing it in 2D, but equally applicable to 3D, okay? Because I'm doing it in 2D because I'll only need to look at the carrier flow in one direction here. So let's assume that L is much smaller than the absorption length. I know L absorption. Okay, so L is much smaller than L absorption. So because I'm shining light, right, there is going to be an absorption length. Light is going to be absorbed at a certain rate, which is given with the absorption coefficient of the semiconductor. And then if your device length is much smaller, then you can assume that this implies light is uniform. Okay, uniform across the semiconductor. There is no spatial dependence. Okay, that's why we are assuming that the length of the semiconductor is equal. So basically, at each point in this device, you have the same amount of light that is incident. So same amount of electron-hole pairs. So essentially, this implies that uniform generation. And if uniform generation is happening, okay, uniform generation implies no spatial dependence. Just a different way of saying the same thing. So the diffusion term is going to go to 0. All right. And I'm also saying that this is a steady state problem, by which I mean that I have turned on light and I'm waiting for some time till everything stabilizes. Okay. It's not the same as equilibrium. Okay. Because once you introduce electron hole pairs by using light, there is an excess minority carrier density, and then there is some recombination, right? So light is driving the creation of excess minority carriers, and recombination is actually reducing it. So there's a certain equilibrium, there is certain steady value of electron hole pairs reached, and that's why we will say that we are saying that it is that steady state. So essentially there is no change with respect to time. Okay, so basically what I'll say is this one, steady state implies no time dependence. Okay, of delta P. Now I'm talking in n-type semiconductor, so delta P is no time dependence, so that's why it is there. Okay, so that's it. We have everything that we need to solve this particular situation. So what does MCD reduce to? Well, MCD becomes the minority carrier diffusion equation. MCDE becomes well, take the other side. So basically, delta P. I mean, there's no time dependence. There's no space dependence. So I can simply write it as delta P equal to GP times tau P. Okay. Let's say I'm having light, right? Generation rate of light generated electron hole pairs. G, I'll write it as lights. This is equal to GP, the rate at which holes are generated, is going to be, let's say, 10 power 17 centimeter cube per second. Okay, this is the rate at which I'm generating. So what is the minority carrier density? Delta P is going to be what? You might think that it is 10 power 17, but no, there is a recombination process which is going to result in a steady state. So the amount of excess minority carrier density is going to be, I have to also tell you what is tau, right? So let's say tau is 10 power minus 6 seconds. This is a kind of large number, I would say, largest number. Typically the lifetime is going to be smaller. Okay. So then this will be 10 power 17 multiplied by 10 power minus 6. So you have 10 power 11 centimeters cube. So you have this much of minority carrier density in the semiconductor. Okay. So you could actually, how does that depend on position? Well, if you take this as the semiconductor, if I plot delta P versus X, what is it going to be? Well, it's going to be a uniform generation, right? So there is no spatial dependence. Delta P is going to be, in this case, 10 power 11 per centimeter cube. Okay? I want you to appreciate this, that even though the rate of generation is 10 power 17 in my case, in the steady state, the net excess minority carrier is going to be 10 power 11. Okay. So this is essentially the net excess minority carriers. Remember, this is happening because we have continuously the light on. If you switch off the light, immediately, it will start decaying and then you'll go to zero. You should have the physical picture. Okay, equation is simply telling you the physical picture. If you're understanding the physical description of the problem, then equations are very easy to apply, not the other way around. Okay, it's difficult to decode the physics from the equation, but the other way around is very simple. Okay, all right. So this is the first case where fairly simple. Now let me take the second case, where I'll say that my length of the semiconductor is large compared to the absorption length. So what I'll do is, now I'll take a semiconductor which is long. Ouch. I wanted a rectangle. Let me do it one more time. Okay. So now my length is going to be L is going to be greater than L absorption. Okay. Much greater. So what I'm trying to say is, when you shine light, for example, let me say I'll shine light now this side, just very easy. All my photons are going to be absorbed only at x equal to 0. Okay, this let's say is x equal to 0. All photons are absorbed at x equal to 0. What I'm trying to say is the length is much longer. Let's say the photon has an absorption length of, let's say, 1 micrometer or something like that. If you're considering 10 microns or 1 millimeter sample, then essentially you could take the absorption is happening only at x equal to 0. Okay, that's why the long sample, and it is still steady state. So what happens? Okay, you turned on the light and then see you want to watch what happens. Okay, well, one important point is we don't have to worry about, we are simplifying the problem. We are assuming that the light is not penetrating into the sample. Okay, so there is no generation. Okay, so 0 within the sample, right? Within sample, there is no generation. But still, depending on the extent of generation rate at delta p, right? Delta p at x equal to 0 is going to be some number. It is still going to be, if you have a rate of 10 power, let's say 10 power 17, that's what we took last time, right? We took 10 power 17. So let's check the same numbers. 10 power 17 into tau p is going to be 10 power minus 6. So we will have 10 power 11 centimeter cube concentration at x equal to 0. Right? We are shining that it's getting absorbed all of it, and it's creating some sort of a, at x equal to 0, we'll have this much of excess minority carriers, right? So now what happens within the sample? So this is the rate at which the photons are coming, and then that's generating an excess steady state number of 10 power 11. Okay. So now previously we had 10 power 12, not 10 power 11. Okay. All right. So what happens now? So you're generating this, huge number of minority carriers. In this case, holes are being generated here. What happens? Of course, they're going to diffuse, right? So we want to solve the equation in the semiconductor. So to solve the semiconductor in the semiconductor at steady state, we turn on and we just wait for some time. We don't do anything. Okay, we wait for some time. When we do that, this is basically steady state. Steady state. So this is going to go to 0. This expression is going to go to 0 because steady state. Okay. I should write it in a different way. This goes to 0 because steady state. All right. So now our MCDE becomes what? The second derivative with respect to position. So I'll write it as delta P. Now this can depend on position, right? Delta P is going to depend on position. The time dependence is gone, but there is still position dependence. I can write it as partial derivative or even the full derivative. It doesn't really matter. Okay. And I'll take the recombination term on the right side. So basically I can write it as delta P of x divided by tau P. Okay. Of course, there is a diffusion coefficient here. Okay, this is my MCDE now. Simplified, right? Simplified MCDE. So now what I'll do is, I'll actually move this guy, dP, I'll put him in here, okay, in the denominator. So now what happens is, what are the units? Think about the units of the denominator here. By dimensionality, you should already see that it should have a position square, but let's just see that. So this is good. dP is going to be diffusion coefficient, so centimeter square per second times second, right? Tau P seconds. So you should have a centimeter square units, okay? So now what I'll do is, I'll define this, okay? I'll define quantity which I'll call as define diffusion length, LP. I'll define it as square root of dP times tau P. Okay, so this is this diffusion length is going to be an important part of my problems. Okay, so please remember, So this is going to have a units of centimeter. Always remember, in semiconductor device physics, the convention is that we use centimeters per length. Okay, we don't use meters. This is a strange convention, but all the textbooks use it, and it's been historical reasons. It's much more common. Okay, so this is going to be having centimeters units. Okay, units of centimeter. Okay, all right. So now what happens to this equation? Okay, this equation now becomes delta p divided by x square equal to delta p by L square. Okay, so I can solve this. Well, when I say I can solve this, I won't solve it, but I'll tell you the general solution. You should have solved this in some of your ordinary differential equations course. If you have not done that, just verify that this solution is correct. Delta p is going to be a exponential minus x by Lp plus b exponential, well, I'll put it, plus b exponential plus x by Lp. This is a general solution that is allowed, okay, for the equation. You can verify it, Yeah, take a second derivative in respect to position, you'll see that, it's coming out to be this. Okay, so the problem will be which of the coefficients is allowed, A or B, okay. So now we are shining light on the x equal to 0. If you allow the second coefficient to be there, if this goes to 0 essentially, let me summarize. B goes to 0 because as x tends to infinity, delta p has to tend to 0 because you're only having light at the left edge. As you go farther into semiconductor, the carrier concentration has to drop. Okay, so because of that, B has to be 0. Okay, therefore B is 0. Okay, so only term that is remaining is A term. Okay, and we can find out how to solve for it. Okay, so let's do that. Let's say our equation has turned out. I just write it. Delta P of x is equal to A times exponential minus x by Lp. Okay, so A is going to be, now we know that delta P x equal to 0 was what, 10 power 11 per centimeter cube, right? That's what we did. This is 10 power 11. We substitute that. So essentially you're going to get delta P of x is going to be 10 power 11 exponential minus x by Lp. So what does this tell us? How do the semiconductors, how does the distribution of minority carriers look like? So well, you take this, you plot it as a position of x. This position x, and this is delta p. You're going to have an exponential pk. Fantastic. I mean, one of the simplest things that we can think of, but delta p naught, right? This is equal to 10 power 11. 10 power 11 here. And as you go, we define the diffusion length. Now we can define the diffusion length as the position as x at which the minority carrier, excess minority carrier concentration falls to 1 over E, right? When it becomes 33%, right? So that is when, this is 0.33, right? 36, sorry. Something. So when basically 1 over E times delta P naught, right? So if you have this, then I think that is a diffusion length. Essentially, your minority carriers are decaying over a certain distance. And what is this number? How much is this length? Let's try to estimate. Okay, we said Lp was square root of dp times tau p, right? Well, I mean dp. What was diffusion coefficient? So remember, diffusion coefficient was dp by mu p was equal to kt by q, Einstein relation, right? And mu p was about, I think, 480, mu. P was 480 centimeter square per volt second. This is the mobility of holes. You multiply it by 0.0256 or 259, you should get it. And so dP is going to be 480 times 0.0259. It will be something in the range of, if I'm right, 10 to 10 or something. Okay, let's assume it to be 10 centimeters square per second. Just you can verify this. I don't want to calculate this. Okay. So now with this, what will happen? Your LP is going to be square root of 10 times 10 power minus 6, right? So for minus 6, so it's going to be 3 point something, 3 point something, let's say 3 point x into 10 power minus 3 centimeters. Remember, this is always centimeters. So you have to put additional thing. So it will be approximately some 30 micrometers. Okay. So this is actually a quite large number. As I said, the minority carrier lifetime is going to be smaller, 10 power minus 9 something. It depends on the semiconductor. If you have a indirect semiconductor, this might be long. Direct semiconductor will be small. So it will be sample dependent, but it's not necessary right now for us. Okay. So what this is telling us is, if you introduce minority carriers over a 10 microns, 10 to 20, 30 microns range, they will all decay. You're not going to see the effect of these minority carriers deep in the semiconductor. It's going to be close to the surface. Okay. And we will see that in PN junctions, the minority carrier diffusion is going to be close to the junction itself. Okay. So that's why we introduced this. All right. So, well, yeah, I'm running out of time, already 50 minutes. Let me quickly wrap up. So the third case I wanted to discuss was a transient case. Let's say there is no spatial variation. We have talked about it in a in different way. There is no spatial variation, so this is going to go to 0. I'll just quickly do this. I'm not going to spend as much time. And then there is no generation. Okay. Well, what it means is, let's say I'll take a sample. I'll take a sample. I'll shine it with photons uniformly. Okay, so that there is no spatial variation. And then at time t equal to 0, I'll switch it off. Okay, so at t equal to 0, light is turned off. Right. So we already said that it's going to exponentially decay, and the coefficient, the time constant is tau p. Right? I just want to show you that. Okay. So before basically what happens at t less than 0, basically light is on, right? It's going to be in the steady state. You can solve the problem. Same time, we have done it a couple of times already. So there is steady state for time less than 0, and therefore delta p, I should not use capital P, small p, delta p, t less than 0 is going to be simply generation rate, Gp times tau p. Let's assume the same generation rates. We were using what? 10 power 17 times 10 power minus 6. It's going to be 10 power 11 per centimeter, 10 power 11 centimeter cube. This is at time less than t equal to 0. Now, for t greater than 0, G light is going to 0, right? I mean, it's basically not creating any electron hole pair, so Gp is going to be 0. Okay. Whether I say Gp, Gl, it's all, when I say Gl, it's light generated carriers. It's going to produce electrons and holes. And the rate at which electrons are being produced or holes are being produced is going to be Gp. Same thing. Okay. So what is this? At time t equal Gp equal to 0. So essentially your diffusion equation MCDE, right? MCDE becomes partial derivative of excess minority carrier density with respect to time. That should be equal to minus delta P by tau P. Other terms are going to 0. So you can solve this, and this solution turns out to be delta P is equal to delta, let's say P naught at time t equal to 0, whatever that is, exponential minus T by tau P. Okay. So you can show these things. Okay, you can you can solve it if you are interested. Just take some moments and solve it. It's not very difficult equations. So I have as a function of time, and this is as a function of delta. So y-axis is delta p. So you're going to have an exponential decay, and that's what we have shown earlier. Actually, this one already tau p. Okay, so this is in our case example 10 power 11. This is some time. We got 1 microsecond or something, right? 1 microsecond. Tau p equal to 1 microsecond. Anyway, you'll see that what happens. All right. So this is a already we have solved this case. So I just quickly went over this. So you can take some examples. Well, this is basically excess carriers as a function of time. Okay, the same problem just we did. I want you to work out. Okay, so we saw that the equation is going to be one small difference here. This is a delta n is given to you. That means we are talking about a p-type semiconductor. Remember, this is p-type semiconductor. Because we are only talking about minority carriers, so p-type semiconductor. So the minority carriers are basically going to be delta n, right? Delta n naught is given to you as 10 power 15, right? So and you're switching off the light. So essentially it is going to be delta n is going to be 10 power 15 exponential minus t by tau n naught is basically 10 power minus 6, right? This is the time. So please find out, okay, what it is. I'll tell you. The simple case is t equal to 0 and delta n. What is it? Okay. So of course, t equal to 0. I'll do this for you. 10 power 15, right? What happens at t equal to 1 microsecond? What happens at t equal to 10 microseconds? Put in some numbers and calculate. Okay. And you'll see that quickly in 10 microseconds, nothing will be left. I mean, you will reach basically the n naught, whatever it is. Okay? This excess minority carrier is going to become 0, almost 0. Check it out. Okay. Check it out what happens. Negligible compared to the original starting point. Okay. So as you know, even 100 microseconds, maybe you should check it out. Okay. What happens? Okay. As you go to longer and longer times, delta p is going to become 0. All right. So this is basically how you calculate minority carrier lifetimes and diffusion lengths. Okay. These are very, very important. And in the end, I just want to show you if you have a combination of both. So far we have done problems with spatial dependence or time dependence, but if you combine both, you could solve it. Okay. I just it becomes mathematically a little bit more involved. But the idea is that you start with, let's say I introduce the same problem as we started with. I take a piece of semiconductor, I shine light at a location x equal to 0, okay, and I switch off the pulse. What happens? So originally you have this position dependence, exactly you created that, that many electron hole pairs. But as time progresses, this is basically as a function of time, you see here, as 10 1 millisecond, 10 milliseconds and 100 milliseconds. As you go in longer and longer in time, you see that the profile is becoming spread out. Okay, so there is diffusion process. This is basically because of diffusion. Okay, and also there's going to be some recombination happening, which will essentially reduce the total area under the curve. If you calculate the area under the curve, that will tell you the total number of carriers, and you'll see that eventually that becomes 0 as you go to longer and longer times, essentially indicating that all the electron hole pairs are getting annihilated. Okay, so I mean, this is not. This is basically, it's going to make sense qualitatively. It should make sense to you. There are numbers which I think is not really necessary for this course. In an advanced course, maybe we could talk about it. All right. So already 58 minutes. I would like to stop here now. So yeah. So today we talked about one very important concept of non-equilibrium dynamics. So we see that in all our semiconductor devices, we are going to introduce some electron hole pairs. Right. We are going to disturb it from equilibrium. Equilibrium is that it exists without any external stimulus. Once you disturb it with an external stimulus, be it voltage or optical light or something like that, so it's going to change the minority carrier density, and that is going to be captured by the diffusion length and the diffusion time. Okay, minority carrier lifetime. Okay? These are very, very important parameters. Please make sure that you're comfortable with. What do you mean by diffusion length, LP, right? So, okay, I'll write it. So please make sure that you're comfortable with minority carrier diffusion length and minority carrier lifetime. Okay, minority lifetime. This we called as tau and this we called as L. Okay. If you're talking of p-type semiconductor, you talk of tau n and ln, and vice versa for n-type semiconductor. Okay. So, all right. Uh, with that, I would like to stop. Thank you very much for your attention. I'm sorry it took a little longer, but I just wanted to get a completeness in this picture. Okay. So in the next lecture, we will talk about, we'll introduce what are known as quasi-Fermi levels, and we'll maybe talk about a little bit about fabrication. And with that, we would have completed the initial toolbox that we wanted to build for understanding semiconductor devices. So starting next week, we will talk about PN junctions, okay, which are one of the simplest semiconductor devices possible. So thank you very much. Have a good day. I'll see you in the next lecture.